So to solve the problems like exercise 7a question 2, what I normally do is I'll rewrite the base so that it's raised to a power that will cancel with the denominator of the power that's already there. So I'll be looking for a number that 32 can be written as something to the power of 5 so that the 5 will cancel with this. So again, 32 written as something to the power of 5, so the 5 will cancel here, and 8 written as something to the power of 3, so that the 3 will cancel here. I'll go ahead and do those for you. Okay, so you can see that I've written the 32 as 2 to the power of 5. Now when I use my index laws on this, it becomes 2 to the 5 times 2/5. The 5s will cancel and I'm left with 2 squared, which is 4. In the second example, I've written minus 32 as minus 2 to the power of 5. So if you do minus 2 to the power of 5, you get minus 32. Again, using your index laws, the powers will multiply and cancel so that you get minus 2 all squared to give you 4. For E, I've written minus 8 as minus 2 to the power of 3. Again, we're going to use our index laws and multiply the powers. The 3's will cancel. And you'll get minus 2 to the power of 5, which we know is minus 32. So for this question, I'm going to need to sketch the graph to be able to find the domain, the range, and the equation of the asymptotes. I prefer to sketch it first. Okay, so I'm going to write the graph so that I can see exactly what power of x I'm working with here. So the square root of x is x to the power of a half, and then you've got 1 over x to the power of a half, so it's x to the negative a half. So what does that mean for the graph? Well, the negative means that it's a hyperbola. And the even number, as the denominator of the fraction, means it's only the positive side of the hyperbola. So let me draw that. So it's the positive arm of a hyperbola. There are asymptotes on the x-axis, so y is equal to 0, and the y-axis, so x is equal to 0. Our domain is positive real numbers that you can write as from 0 to infinity, not including 0 or that. Don't write both of them in the exam, just write either that or that, and the range is the same. So for this question here, I've actually worked through questions like this in the previous video for 7a, for chapter 7a. If you have a look back through there, if you don't watch the whole thing, it's quite long. If you don't watch the whole thing, at least look at the examples at the end and it will explain what's going on, even just a little bit before the end to see what's going on. But anyway, to sketch this graph, I recognise that the fraction is greater than 1. So the function is going to be parabolic in shape, so I'm going to draw the positive arm for the function. Next, I'm going to check my denominator. The denominator is an odd number. That means that we do have a negative tail, so the graph's going to continue somewhere over here. To determine whether it's in quadrant 3 or quadrant 2, I look at whether the numerator is an odd or an even number. The numerator is an odd number, which means the tail's going to be in quadrant 3. So it's going to be a mirror image reflected of the top part of the graph in quadrant 3. Okay, so that's what my graph looks like. I know that the function itself goes through both 1 and 1 and minus 1 and minus 1. Didn't do that very well, did I? It is symmetric. Now, we need to do the domain for this function. So the domain is real numbers and the range is also real numbers, and it doesn't have any asymptotes. Okay, so this question here is again a power function. We do have a vertical reflection across the x-axis to do at the end, but we will do that, we'll leave that to the end. Any kind of vertical dilation or reflection, just leave that to the end once you've got the normal shape of your graph, and then do any reflections or dilations you need. Okay, so we look at the actual fraction itself. We recognise that 3/5 is less than 1, and so our graph is going to be a root-shaped graph. So I've just dotted in the positive arm of the graph. Then we look at the denominator to see whether it's odd or even. It's odd, which means that a tail exists. And then we look at the numerator, which we see is odd, which tells us that the tail is in quadrant 3. So the tail would sit like this. But we do have a reflection that we need to deal with. So the positive arm reflects, we're going to reflect across the x-axis. So our graph actually comes down this way and then comes up this way. So this is our final graph. This is the graph of f of x is equal to minus x to the 3 on 5. Our domain is real numbers and our range is real numbers. So for 4D, I'm sketching something that looks quite weird. I'm going to rewrite it so that I have it as x to a fractional power. So the cube root of x is x to the power of a third, and the fact that it's 1 over means that it's negative a third. Okay, so now let's sketch it. And to do that, we need to be able to recognise the shape of the graph from the values for the fraction. So our fraction is negative, which means it's going to be a hyperbola. The denominator of our unit fraction is an odd number, which means we're going to have both arms, and the 8 at the front means that we have a vertical dilation, which means for our x is equal to 1 value, the corresponding y value, instead of being 1, will be 8. And for negative 1, instead of being negative 1, it will be negative 8. And so I need to write the domain and the range and include my asymptotes as well. And so there are asymptotes at x is equal to 0 and y is equal to 0. The domain is all real numbers except for 0, as is the range. So for this question here, we're meant to find where the values of x that make x to the power of 3 on 2, the answer to that greater than the answer to x to the power of 2. To do that, I'm actually going to sketch these as two different functions. Then all I need to do is to see where the green function is higher than the yellow function. So I sketch the green function. So the fractional power is greater than 1, which means that the graph itself is going to be parabolic in shape. So I'll put in the parabolic arm for the positive side, and I know that that goes through the point 1, 1. All power functions go through the point 1, 1. Then to determine if there is a left-hand side of the graph, we look at the denominator of the fraction in the power, and we see whether it's odd or even. So we're looking at the number 2, that's an even number, so that means that there is no negative tail for that graph, so that is the full graph. Oh, and I've drawn it in blue instead of green. Let me just fix that. So now I'm going to draw my parabola. Now it might have actually been easier to draw the parabola first, because the difference between the two is just that the power for the green function can actually be written as x to the power of 1.5. And we're comparing it to x to the power of 2. So x to the power of 1.5 will in fact be closer to the line. Draw this line here, make it go through there. That's the line y is equal to x to the power of 1. So x to the power of 1.5 will be closer to the line x is equal to 1 than x is equal to the power x to the power of 2. So it will be closer to the line in the lower half and closer to, the green one will be closer to the blue line in the upper half. So this is x squared, and the other one, the green one, is x to the power of 1.5. And so to find the section of the graph, the domain where the green graph is above the yellow graph, that is this section of the domain here. On those x values, for those x values, the green line is above the yellow line. And so our solution is this domain here. So the actual answer to the question is that x is between 0 and 1, because at the point 0 they're equal, and at the point 1 they're equal. So the green line is only above the yellow line in between that section. I think the answer at the back of the book has that written in interval notation, except it doesn't actually have that x is an element of, I think it just has 0, 1, so that it looks like the point 0, 1. But that's how you do those questions. Okay, for this section we've got our x to the power of 3 on 2 graph again. So I've just gone ahead and drawn that. And this time we're looking for where that graph, the green graph, is less than, and the y values are less than the function x to the power of minus 2, which is in fact a truncus. So let me draw that in. So both of these graphs pass through the point 1, 1. The truncus also passes through the point minus 1, 1. So they intersect at the point 1, 1. And so again, we're looking for the section of the graph, the x values, where above or below, the x values for which the green graph is below the yellow graph, which is going to be this section. Again, in here you can see that in that section, all the way up there, that the green graph is below the yellow graph in that section. And so that section there is the area that we want. Now we can't include 0 for this because there is an asymptote for the hyperbola, so the hyperbola doesn't exist. So we can't actually compare the two graphs at x is equal to 0. So our solution is that x is an element of the open interval of 0 to 1, or you can write it as 0 is less than x is less than 1. We're not including the point here where x is equal to 1 because their actual functions are equal to each other, and we need them to be less than one less than the other.